In this video, we're going to look at electrochemical reactions occurring at non-standard conditions. What we mean by non-standard conditions are that the concentrations of all the solutions are not 1 molar. So normally we assume standard here usually means that all solutions have a concentration of 1 molar. All right. So what happens when we stray from that assumption? Well, it turns out that, so I've drawn our canonical electrochemical cell here using zinc and copper, and we know the electrons go from the anode to the cathode as the zinc is oxidized and the copper is reduced. So if we run this with both solutions at 1 molar, we get the voltage that we've calculated from our standard reduction and oxidation potentials, which is 1.0 volts. And if you're shaky on that, there's some videos earlier in the channel that you can take a look at. However, it turns out that the voltage changes if we start decreasing systematically the copper concentration in our solution over here in our beaker. So the only thing we're going to change in this series of experiments is the concentration of the copper solution. As we go from 1 molar to 0.1 to 0.01 to 0.001 molar, what we see is that the voltage that we record, it decreases. So it's not a large effect, but it is large enough that we can detect this in the lab with just standard voltmeters that we buy from the local hardware store. So something has to be going on here. And there's two ways to look at this. The first way is to think about it in terms of Le Chatelier's principle. We are decreasing the concentration of a reactant. So remember, the zinc and the copper here are solids, and their concentrations don't change. We always plug them in as 1 when we're calculating a Q or a K value, right? So we're going to ignore the zinc and the copper solid. We're just going to look at the copper solution and the zinc solution. So if we systematically decrease the copper concentration, we know that the reaction will tend to lean back a little bit towards the reactants to compensate for that. And so if you imagine, instead of changing solutions here, that you were gradually decreasing the copper solution concentration, this reaction would run in reverse to try to replace that depleted copper. All right, and that is and if the reaction were going in reverse, it would be less favorable than it would be. And so we would expect our E value, our voltage, to decrease towards 0 or even go negative if it were far enough reverse. So so that's the first thing we're going to do. If we could also make this reaction go more strongly in the forward direction by increasing the copper solution concentration, or we could decrease the zinc concentration, would be another way to do it. There is an equation that you can use to predict the E value here, and it's going to look very similar to the delta G equation that the delta G versus delta G naught equation. So the equation is known as the Nerst equation. It is going to be that E is equal to E naught minus R, gas law constant, times temperature, over N, the number of electrons transferred, times Faraday's constant, times the natural log of Q. Q is our old friend from equilibrium, which is products over reactants, same expression as K. In the case of this reaction here, Q would be the zinc concentration, zinc ion concentration, over the copper ion concentration. Again, remembering that zinc solid and copper solid have an effective concentration of 1, as we call it, because they don't change over the course of the reaction. All right. This reaction, or this equation, the Nerst equation, is going to accurately predict the direction of changes here, mainly because this this negative sign here is going to reduce the voltages if our Q is getting larger. In other words, if we have if the reaction is being driven in reverse. So let's go back up here real fast, add a column here for Q. Q would be, again, zinc concentration over copper concentration. So 1 over 1 would be 1. Here we would have 1 over 0.1, that's 10. We'd have 100 for this one and 1,000 for this one, because that's 1 over 0.001. And so each time we're plugging in a larger number here to Q, which makes this negative term get larger and larger. And so a larger number is being subtracted from the E naught value, making the value of E, the non-standard voltage, decrease. You'll see this written a couple of ways. Another way that if we assume the temperature equals 298 Kelvin, which we often do because we're usually measuring these in the lab, the E value is equal to E naught minus a constant 0.0592 over the number of electrons transferred times the log base 10 of Q. Notice that this is the natural log up here. This is the log base 10. And it really doesn't matter which one you use. They'll both give you the same result if you're at 298. And so both of these equations just show, however, that as this Q value gets larger, either because you are increasing the product ions concentration, or reducing the reactant ions concentration, the E naught value is going to go down. One other thing to note here is that this is the reason actually that that batteries go dead, as we say, because what happens here is that you either use up all of the you've either used up too much of the copper or created too much of the zinc 2+ ions. And as you do that, Q gets larger and larger over time, and eventually your voltage drops below some useful value. And so our standard 1.5 volt AA or AAA batteries will gradually, their voltage will decrease over time until they become useless, just because of the fact that the reaction is producing more of the product ions and it's consuming those reactant ions, and that causes the value of Q to increase over time. So if we're looking at electrochemical reactions at non-standard conditions, we can either use Le Chatelier's principle to predict the direction of the change for E, or we can, if we know the values, we can plug them in to the Nerst equation and solve for them and get the values of E that we would see here.